So here is the photoelectron spectrum of methane. And so let's go and break this down. The first thing that you'll notice here is there's two peaks, right? One at centered around 15 electron volts. The other smaller peak centered around 23 electron volts. So how do we interpret this? We have to go to the molecular orbital diagram, right? So we constructed this earlier in the chapter and saw that contrary to what we might think from a simple Lewis structure via CPR analysis, we have electrons in orbitals at two different energy states. And lo and behold, right, they have two different states. There's two electrons in the lower energy state, and there are three electrons in the six electrons in the higher energy state. So we expect these to be in a 1 to 3 ratio or 3 to 1 ratio. And if you look at this, right, the bigger peak occurring around 15, right, that corresponds to the T2 because we have the peaks in a 3 to 1 ratio. And the higher energy peak, right, it was more stabilized, A1, it was more stabilized right here. So it took more energy to eject the electron out of it. That's going to be where the one that you have, 1/3 of the number of electrons in. So the peak area will correspond like this, okay? Just like in NMR spectroscopy or a lot of other spectroscopies, your peak intensity is meaningful, right? The integral is meaningful here. And so that's kind of nice. We can take a moment to reflect on the energies. And what energies do we really know here? Well, we know that this is 13.6. This came from just the ionization energy of hydrogen, 1s orbital. And so whatever T2 is, it was a bonding orbital formed from 13.6. So it should be less, more stabilized than 13.6, and it is, right? It's around 15. And then this one, A1, is about 23. So it should be less than the ionization energy of the 2s orbital of carbon, which was 19.5. So it's more stabilized, right? It's at 23 versus 19.5. So all these things make sense. So, really, this is the proof in the pudding right here that VSEPR gets it all wrong, and Lewis structures get it all wrong when it comes to energetics, right? Clearly, this is a very simple experiment, and you have two different energy states, and the molecular orbital diagram predicts this perfectly, okay? Let's think a little bit about the peak shape. What do we expect? Well, these are both bonding molecular orbitals. Because they're both bonding molecular orbitals, we know from our first rule on peak shapes that we went over in the last video that if you're a bonding or an anti-bonding molecular orbital, you're going to give rise to vibrational structure. And so both of these have vibrational structure. The second thing we know is that you can have further splitting that goes on when you have degenerate orbitals due to spin-orbit coupling for heavier atoms, preferentially, or Jahn-Teller effect for lighter atoms. We are on relatively light atoms, right? I mean, carbon is in the second row, hydrogen is in the first row, so we're in light atoms here. So we don't really expect spin-orbit coupling to be a big deal, but Jahn-Teller effect should be operative here. And for the A1 molecular orbital, that shouldn't happen because there's no degeneracy. So if you look at the A1, sort of just looks like a singlet, right? With no real splitting other than the fine structure, the vibrational fine structure. If you look at this T2, right, peak, you can clearly kind of see a doublet, right? And of course, on top of it, there's all the fine structure. That doublet is coming from Jahn-Teller effect, the Jahn-Teller effect, because we have a degenerate orbital there. So let's look at sort of a periodic series. We love periodic trends, especially as inorganic chemists, because you get to use the whole periodic table. It's the best thing about being an organic chemist, So let's look at methane, silane, germane, and stannane. First thing to look at is the ionization energies, so that we can think about how the molecular orbital diagrams would change, right? Because the ionization energies tell us about the energetics of the atomic orbitals from which we construct the molecular orbitals. So as we expect, as we go down the periodic table, the ionization energies get less. Why is that? Well, they're less electronegative. That's the easiest way to think about this. So the electrons are not held as tightly. You can think about less electronegative, or just they're bigger orbitals, further away from the nucleus, easier to eject. And so you can see that, you know, this is true for p orbital very nicely. You go 10.7 for carbon, 7.8 when you get to the 3p for silicon, a 4p for germanium, 7.6. It's sort of true for carbon, silicon, and germanium. And there's something, you can see 19.5 down to 15 from going to 2s to 3s. It goes back up slightly when you get to germanium, 4s. This is something called the inner pair effect. It's not really that important, but basically it's some screening that is caused by the 3d electrons, right? This is a 4s, so there's 3d electrons. Silicon didn't have 3d electrons there. And so there's just a lot of electrons there. If you go back down to 5s, stannane, it will continue the trend as you expect, okay? So it's just kind of this jump from the second row to the third row with the s orbitals here. Not important. General trend is that the ionization energies tends to decrease going down a family. And so here are the spectrum that I pulled from an old book. And so first thing to notice is that the bonding orbitals are less stabilized. I mean, first things first, right? There's still two sets of peaks, okay? And why is that? You still have the A1 peak over here, right? And you still have the T2 peak over there. But now you can start looking at more subtle changes, right? One of the subtle changes is that the bonding orbitals are less stabilized. You see, this is at 23. This is more 18.5, 18.5, 17, 14, you know, 12 and a half, kind of around 12 and a half, and then 11 and a half. Okay, so as we go down the periodic table, we're being less stabilized. So why would that be? Well, lower ionization energies, right? So what is happening, these are getting destabilized. Destabilized means these are going up, right? Less ionization energy. If these are getting up, okay, then the T2, right, which is responsible for much of the bonding, and specifically the T2, right, it's responsible for 3/4 of the bonding. If that's going up, it's getting further away from the salts. The hydrogens aren't carrying, the hydrogen salts, those don't change. We didn't change that. And so if this T2 is further, which is responsible for 3/4 of the bonding, right, and it's getting further away from the salts, when you go and you make the T2 bonding, that's not going to be as stable. It's not going to go down as much. Remember, you have to have similar energy, same symmetry. We have same symmetry, but now as we go down the periodic table, T2 is going up, and so we're getting less and less similar energy, so you get less and less overlap and make a weaker bond. Basically, this energy it rises up. Okay, and so that's what's happening. Okay. Other thing you can see is that the vibrational gaps change. So the fine structure here, the gaps between these different little peaks within the big peak are pretty big for methane. But by the time you get to stannane, they're very small. You can barely resolve them. That makes sense because of our relationship of the vibrational gaps, right? Reduced mass is going up as we go down the periodic table. So this gets bigger, mu gets bigger, causing mu, which is reflective of the gap size of the gaps, that gets smaller. Okay. What else? Spin orbit coupling. We start to see this triplet evolve. Very heavy atom, tin, we're going to have spin orbit coupling. We have a T2 that's a triply degenerate. And we said for spin orbit coupling, triply degenerate molecular orbitals give triplets. So you have this formation, this nice triplet. And germanium, you know, and silicon, they're kind of competition between a little bit of Jahn-Teller, a little bit of spin orbit coupling. Here you're mostly Jahn-Teller, and here you're mostly spin orbit coupling. All right, so you get weaker bonding because of this sort of change, okay? And because you have weaker bonding, this can help you predict some of the physical properties that are different. So if you look at, you know, just what happens, methane is stable. Of course, if you light a match, it catches on fire. Silane, you can spray it into air and it will immediately combust. You don't need a match, so that's pretty reactive. Germane, you just heat it up a little bit in the absence of air and it'll combust, or it doesn't combust if there's no air, but it decomposes. Stannane is not stable at room temperature. And plumbane, which is really unstable, I think was only recently synthesized through some specialized techniques, and it's only stable at very low temperatures. So you see this very clear trend, and all that, you know, is because we have weaker and weaker bonds, and we can explain that with respect to the molecular orbital theory. Again, sort of additional information that you can never see just from a simple Lewis structure, right? So pretty cool stuff, and you know, very important concept in the course, showing why knowing why and showing why molecular orbital theory is more powerful than simple Lewis structures.